Welcome to the next session, my dear friends. In the previous session, we were discussing about the operation of rapid sand filter, and also we have seen in the previous session operation of slow sand filter. So, we are going to discuss the specifications now of a rapid sand filter. Specifications of rapid sand filter. Specifications of rapid sand filter. So the plan area of rapid sand filter varies from 10 to 50 meter square. The plan area of rapid sand filter varies from 10 to 50, or sometimes it may be up to 10 to 100 meter square per unit. This is the plan area. And sand layer depth, sand layer thickness 60 to 75 centimeter, whereas in slow sand filter it is 90 to 110 centimeter. Here the depth of the sand is more because sand is the only filter media we are having, but here in the rapid sand filter, gravel media also helps in filtration. That is why the gravel thickness here, base material gravel depth is 45 centimeter to 60 centimeter. Base material gravel thickness is 45 to 60 centimeter. Base material gravel is 45 to 60 centimeter, and it is laid in 4 layers. And D10 here, D10 is equal to 0.45 to 0.7. So we will establish a comparison between rapid sand filter and slow sand filter later. Okay, these are the specifications of rapid sand filter. Let us see first. And CU, coefficient of uniformity, 1.3 to 1.7. Coefficient of uniformity is 1.3 to 1.7 the material. So in rapid sand filter, better gradation of gravel is necessary because here in this actually base metal gravel laid in 4 layers of different sizes, of different size, because so first point is, I told you already, it also takes some participation in filtration as well as during backwashing. So water is distributed from the gravel layer. So whatever the water into the sand layer, so during backwashing the water needs to be distributed uniformly. For having uniform distribution, proper gradation of gravel layer is necessary. Okay, because during backwashing to distribute water uniformly, wash water uniformly, it is necessary to have proper gradation. It is necessary to have proper gradation. So that is why we lay the gravel in different layers, and the size of the layers are also there, but it is not that necessary. Okay, it is not that necessary. Actually, one layer, first layer 3 to 6 mm, second layer 6 to 12 mm, third layer 12 to 20 mm, and fourth layer is 20 to 40 mm. Likewise, we will fix the sizes of the material but that is not necessary for the gate examination and all. And here length to width of this tank, filtration tank, length to width L by B, approximately it ranges between 1.25 to 1.33, 1.25 to 1.33, and the length in general we keep it is 12 meter and 9 meter. In general length we keep it as 12 meter and width we keep it as 9 meter. In general we keep these values of dimensions to the rapid sand filter. And freeboard, we keep a freeboard of 0.5 meter and depth of the water above the sand layer is 1 to 2 meter. Generally water column we maintain it is 1 to 2 meter, and freeboard we keep it around 0.5 meter. So freeboard 0.5 meter. And water column means if you take a tank, this is sand bed, so this is water column, this is water. So water column depth is, generally the water column depth we keep it around 1.1 to 2 meter. Water above the water column above the sand bed, the water column above sand bed having a depth of 1 to 2 meter. And here also the overall depth of the filter varies from 2.5 to 3.5 meter as it is in the slow sand filter, also the same value. So the maximum the loss of head here, maximum loss of head we allow here is 2.5 to 3 meter. So here the maximum loss of head, because the loss of head here we measure using inverted manometers and all that are being installed in this. So I haven't shown it because it is not necessary where you will locate it and all. So there will be manometers which indicates the loss of head. Generally the maximum loss of head permitted here, the maximum loss of head allowed is 2.5 to 3 meter. 2.5 to 3 meter is the maximum loss of head is allowed. Okay, so backwashing is generally done for about 10 minutes for every 24 hours. Okay, 1 to 3 days actually we need to do backwashing here. We need to do backwashing here for every 1 to 3 days, whereas there for 1 to 3 months we clean the slow sand filter. Here we need to wash it for every 1 to 3 days, at least for about 10 minutes of time. We need to keep the filter in maintenance because it is having more filtration rate, that is about 30 times of filtration rate with comparison with the slow sand filter. So that is why it needs frequent cleaning. It is pumping more water, it is filtering more water. So that is why frequently the filters will get completely choked with the impurities. So that is the reason why we have to clean this for every 24 hours to 3 days, minimum 24 hours, and at a maximum value of 3 days we need to clean it for 10 minutes. That is the 10 minutes we do backwashing. Rest of the time we do normal filtering, and this 10 minutes we will send the water through the bottom under drainage unit with high amount of pressure and velocity. So backwashing, cleaning of filter through backwashing, is done for every 24 to 48 hours or approximately 1 to 3 days. Approximately 1 to 3 days. It is not that you told that it is 1 to 3 days. I am writing it to 24 to 48 hours. So it is a limit approximations. There is not a fixed durations are there, because one filter, depending upon the incoming raw water's quality, the duration varies. Here we can fixedly say that what is the head loss permitted. So 2.5 to 3 is the head loss permitted, whereas this duration may be varying, okay, because depending upon the quality of the raw water, so this duration may vary, right? For every 24 to 48 hours for a duration of 10 minutes. With a backwashing velocity of 5 to 7 times of rate of filtration. With a rate of backwashing, which is 5 to 7 times. 5 to 7 times of rate of filtration. 5 to 7 times of rate of filtration. And we use 2 to 5% of filtered water for cleaning of filter. 2 to 5% of filtered water is for cleaning. So there is another small formula is there to fix up the minimum number of rapid sand filters are needed. Okay, so minimum number of rapid sand filters for a community, minimum number of rapid sand filters needed is equal to, there is a empirical formula, needed is equal to 1.22 square root of q. 1.22 square root of q. 1.22 square root of q, and it should not be less than 2, where q is in mld. Q is in mld, million liters per day. When the q is, the discharge required is given in mld, then 1.22 square root of q is a value by which you can find the number of rapid sand filters that are required for a particular community. Okay, so now we are going to discuss, these are all the specifications of a rapid sand filter. Now we are going to discuss the under drainage system for both, which is present for both slow sand filter and rapid sand filter. But the difference in the under drainage system between these two, slow sand filter and rapid sand filter, is in slow sand filter under drainage system only collects the water, whereas in rapid sand filter under drainage system should be sufficient to collect the water, as well as it should be having a capability for backwashing also. So both will be done along the under drainage system. In case of rapid sand filter, backwashing is also necessary, whereas in case of slow sand filter, only collecting the water and send it to the outlet is the only work of the under drainage system. Okay, so let us see how do we design the under drainage system. Whatever be the activity it perform, the requirement of the material and arrangement of the material is same, right? So generally under drainage system, okay. Now here, if you observe under drainage system, it will be like this. So this is plan area, the bottom plan area of the filter, the bottom plan area, top view. So there will be perforations at the bottom. There will be perforations at the bottom, that is called lateral. Those are called laterals. See, these are all laterals. So that means, see, if this is a filter, if you look at the filter like this, this is a filter, okay? So this is the bottom plan area, whatever I am telling, this is the bottom plan area. So in this bottom plan area, so there will be an arrangement like this. So these are called laterals. So whatever the things which you are seeing, these are called laterals. These are called laterals. And whenever the water is going down, okay, so that will come onto this lateral. So these laterals will have a perforations. If you look at the lateral, see, lateral will be like this. Laterals, if you look at from this side view, okay, if I am looking from the side view point of view, then how it looks. So these are the laterals. One lateral for one side, one lateral for other side. And these laterals will have the perforations on it, openings. These are pipes. These are pipes simply. If you look at the these are like a pipes. So now here what happens? So in these pipes, the water, whatever the water coming, filtered water will enter. These pipes are opened only top. It won't be open in the bottom. If it is open in the bottom, it will go out. It won't enter into the central drain. So whatever the water coming from the filtration, that will enter the perforations. From the perforations, it enters into the pipe and it travels like this. It enters into a central drain. This is a central drain. This is central drain. So through this central drain, so this central drain will have a slope either one side or other side from where you want to take the water out. So in that direction you need to keep the slope of the central drain. So using this central drain we will take the water out of the filter. So this is how is the arrangement. Laterals are connected to central drain and laterals will have perforations which take water from the filter, and this is how the mechanism works of collection of water and transporting the water out of the filter. So this is the mechanism of how it works. How to design this mechanism, that is what I am explaining it here. How to design that mechanism, that we are going to discuss it here. So these are the laterals. So this is central drain. So there are some caudal specifications. There are some caudal specifications to design this. First one is perforation size. Perforation size. So there are perforations I have told you on the top. So perforation size. The size may be vary from either diameter, either we can keep it as 5 mm or 12 mm or 12 mm. If it is 5 mm, then the center to center spacing of the perforations, center to center spacing of perforation should be 8 centimeter. So center to center spacing of perforations is kept as 8 centimeters, and if it is 12 centimeter, it is kept as 20 centimeter. So perforation sizes, either we keep 5 mm or we keep 12 mm. If it is 5 mm, then the spacing is 8 centimeter between the center to center. So this is one perforation, this is another perforation. This is called center to center, okay, spacing of perforations. That is 8 centimeter for 5 centimeter and 20 centimeter for 12 centimeter. Cross section area of the perforations. Cross section area of perforation should be equal to 0.3 percentage of total filter area, So whatever the filter area we are having, in that 30% area we will take, that 30% area should be equal to the cross section, total sum of the cross section areas of the perforations, So we know diameter of the perforation, we will fix up diameter of the perforation, and then this diameter will give you single perforation area. So this is the total perforation area we need, so that we will get to know what is the total number of perforations needed from these two data. So total number of perforations we can find using these two data, and depending on that we will fix up how many laterals are needed. So again, to design lateral, so cross section area of a lateral is equal to 2 to 4 times of cross section area of perforation of each lateral, 2 to 4 times of cross sectional area of perforations. So 2 to 4 times of cross section area of perforation, we take it as cross section area of each lateral, okay. Now once we get to know the cross section area of each lateral, and generally we adopt D is equal to 5 mm when the perforation size, when D is equal to 5 mm, we take 4 times of cross section area. Here cross section area of each lateral is 2 to 4 times of cross section area of perforation. Again, there are two variants of cross section area of perforations. One is 5 mm, another one is 12 mm. So when it is 5 mm, we adopt 4 times of cross section area of the lateral we will take, okay. We adopt 4 times cross section area of perforation. So when it is lesser diameter, then we take more number of times. When D is 12 mm, we adopt 2 times cross section area of perforations. That is nothing but the lateral cross sectional area. Okay. Now here we have known this lateral cross section area and cross section area of perforations, total number of perforations we know the spacing of the perforations. Similarly, we will know, so this is the cross section area of each lateral, then we will understand how many laterals are needed depending upon the number of perforations needed. So if one lateral is getting these many perforations, then to accommodate some n number of perforations, we have already determined from here some n number of perforations we need. So how many this type of laterals are needed on one side, this type of laterals are needed on other side, that we will find using the total number of perforations is necessary, okay. And next is cross section area of manifold or the central drain, cross sectional area of central drain or manifold is 2 times the cross section area, 2 times the cross section area of the perforation, 2 times the cross section area of the lateral, 2 times whatever the cross section area of lateral you got, 2 times of it, because from 2 sides it is coming. 2 times the cross section area of laterals, because so here the central drain is getting water from 2 laterals at a time. So that is why, so the central drain cross sectional area should be such that it can accommodate 2 cross sectional areas of laterals at a time. So that is why we need the central drain cross section area should be 2 times of the cross section area of the lateral. Okay, 2 times of the cross section area of the lateral. Here if the depth of the sand bed is D, okay, so if the depth of the sand bed, I will explain it by drawing a figure. So these are the system, these are the design of under drainage system. Let us just repeat it again. So first we need to fix the perforation size. So perforation size, we are having 2 diameters here possible. One is 5 mm diameter and 12 mm diameter. If it is 5 mm, then the center to center spacing is 8 centimeter, and if it is 12 mm, the center to center spacing is 20 centimeter. This is, from here we will get individual perforations area, individual perforation cross section area we will get, and cross section area of total perforations is 0.3 times of total filter area, that is 30 times of what filter area. From where you will get the total perforation size. So total by individual will give you number of perforations. So number of perforation needed is equal to total cross sectional area, of perforations, that is 30% of filter area by area of, that is area of individual perforation. So this is the formula for total number of perforations. So once you get to know the total number of perforations, we will keep it aside and we will determine the cross sectional area of each lateral. Each lateral is equal to 2 to 4 times of cross section area of perforation. So here we know the cross section area of each perforation. So if it is 5 mm, we need to take the lateral area is 4 times the area of the perforation, and if it is 12 mm, then we need to take 2 times the area of the perforation. Okay, and also area of the central drain, we will take it as 2 times the lateral area. Area of the central drain is 2 times the laterals area, and number of laterals depends on each lateral how many holes we can accommodate. So if you know the length of the lateral, so then how many holes that can be accommodated. So length of the lateral we can find, I will explain you how to find the length of lateral. So before moving into that, there is another thing we need to know. If we are sending backwashing water, okay, so if you are sending backwashing water, that means the water will move through the sand filter media with high velocity or with high pressure. Okay, so here we are sending the water for backwashing through the sand media either by high velocity or by high pressure, right? So during this process, the sand bed faces some thrust from the bottom. Okay, the sand will face some thrust from the bottom because of this velocity head or because of the pressure head. Both will create some thrust on the sand media, which causes the expansion of the sand media, right? So now when the sand media expands, then how it looks? See, generally these are the wastewater troughs. These are the wastewater troughs which are above the sand filter media, and this is the depth of the sand. This is the depth of the sand. This is the depth of the, let D is the depth of the sand. If the depth of the sand is D, then the wash water trough should be at a height of D by 2 above the sand bed. Okay, so it should be at least the height of the trough. So this should be more than D by 2. It should be more than or equal to, greater than or equal to D by 2, because how we design is, when we backwash the filter, so generally it will try to expand the filter media. Because whenever we are sending water from the bottom, this filter media will expand. So this layer will expand. This layer will expand like this. So it expands by a maximum value of 50%. During backwashing. That means this D will become D plus D by 2 during the backwashing. So during backwashing, so the layer, during backwashing, the filter media expands. By 50%, and hence the wastewater trough should be kept at least at a height of D by 2 or even more. The wastewater troughs, the wash water troughs, or else we can call it as wash water troughs. Wash water trough should be kept at a minimum height of D by 2 from filter media. So likewise, generally we need to keep the depth of the wash water trough. We need to keep the this wash water trough depth. And also, if you look at the laterals, there will be perforations, right? So here the perforations, if you look at the laterals like this, so this is laterals and these are the perforations. These perforations, if you look at in other plan, so these perforations sometimes may have strainers on it. So these are called strainers. That means a net kind of a porous member, okay, through which we send the water. That is nothing but strainer. Generally, if you are sending the water, if you are using backwashing, if you are doing backwashing with the pressure, compressed air, then generally we need this kind of strainer arrangement. Strainers are needed on the type of perforations. Strainers type of perforations needed during slow velocity backwashing. So, or else if you are doing high velocity backwashing, then it is not that important to have the strainer. Okay. So, but a strainer kind of lateral is used for slow velocity. So, we are sending compressed air also through this. So, lateral, that is why it is necessary to have the strainers to have uniform distribution of the compressed air. We need strainer, whereas these strainers are not needed in case of high velocity backwashing. Okay, in case of high velocity backwashing. And one more thing, how to find the length of the lateral, and also we need to check the safety of the lateral in terms of buckling, because the length of the lateral is more and the width of the lateral is very less, right? So the length of the lateral is very high and the width of the diameter is nothing but the width of the lateral, so it is very less. That is why it may be prone for buckling. So we need to check for buckling wherever you go. If the member is lean, slender, then it is prone for buckling. So we need to check for buckling. We need to design it safer for buckling. Okay, that is what we need to do. So here this is the width of the filter, completely plan area. This is the plan area, and this is the length of the filter, and this is the width of the filter, and this is a central portion, right? This is central portion. So the lateral length is nothing but generally B. This is B. Okay, B. So length of lateral is equal to B minus, if this is the diameter of the manifold, is dm. Okay, so let dm is diameter of manifold or central drain. Okay, d is the diameter of the manifold or central drain. Now B minus dm is the width, this plus this. So deducting dm, we will get the width, this plus this. So it is sum of length of the two laterals. So this one and this one, both. So we want only one lateral, then we need to divide it with 2. Then we will get the length of each lateral. Isn't it? Length of each lateral. Again, if you look at the cross section, generally the length of the lateral, approximately we are taking it as this, but if you look at the reality, lateral is inclined. So laterals will be inclined like this. Okay, so if the lateral is inclined, that means we are taking this as, this is B minus dm by 2, but this is the length. Actually, if you go precisely, then we need to take the length, that if you know the theta, we can find the length of the lateral. If the theta is given here, for example, if I take it as a line diagram, so take it like a line diagram. So this is central point, and this is the location where we are having central drain. So this one is B minus dm by 2. If you know the angle theta, okay, if we know the angle theta, this is length, actual length is this. If you know the angle theta, so we can find a length of lateral. once we know the length of the lateral, we can check the safety of the lateral against buckling. So here the safety of the lateral, against buckling. So if the length of lateral by least dimension of the lateral, length of lateral by diameter, that is the least dimension of the lateral. Okay, dia of lateral should not be more than 60. Then it is safe against buckling. So these are the things which we need to ensure in the under drainage system. The rate of backwashing, generally how to fix the rate of backwashing and how to calculate the force of backwash on the filter media, and how the filter media will get affected due to backwashing. See, during the backwashing, what we need to do is we need to ensure that the impurity present inside the filter media should go out. The impurities present inside the filter media should go out, but the filter media does not go out. Our planning should be such that, see here, one important aspect of backwashing which we need to understand is so the important aspect of the backwashing we need to understand is, so there will be impurity, there will be sand particle. Okay, there will be impurity as well as there will be sand particle. So sand particle of the filter media, if you take a sand particle, okay, this is filter media particle. Okay, this filter media particle will have its self weight, gravitational force. It will be having self weight, and on this filter particle we are applying backwashing force. Okay, so this backwashing force, this is called force of backwashing should be sufficient to remove the minimum size of the particle, it should be sufficient to remove the smallest impurity also present in the filter media, but it should not remove the filter media particle. So very typical task is this. So we need to how to fix this force of backwash, because when you are sending water from the bottom onto the sand media, okay, now you are working in the opposite direction of gravity on that filter media to just take the impurities out of the filter media. Now during this process, so if you don't design the force of backwash properly, then all the sand media also go out of the filter media as an impurity. So we are here to safeguard the filter media, and we need to only remove the impurities present inside the filter media. That is very, very important. So how to do that and how to design all these things, okay, how to find the force of backwash without affecting the sand particles, and also how this bed is expanding, and what are the concepts that are present in expanded bed and all, we will discuss in the next class. Thank you so much.